Hello everyone, geometry, circles and polygons. This is actually unit 4. Lesson number 1. Our essential learning goals for today are to be able to define and draw a diagonal, recognize the difference between equilateral, equiangular, and regular polygons, as well as classify polygons up to 12 sides. Let's get started. A polygon is a closed figure in a plane formed by connecting line segments endpoint to endpoint with each segment intersecting exactly two others. So each of the following here to the left are polygons. You can see this is a three-sided polygon. We call that a triangle. We've got a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12-sided polygon. A 5-sided polygon called a pentagon. And then over here you can see that we have non-polygons or not polygons. Okay, this line right here, line segment, does not enclose a space, therefore it's not a polygon. This shape here encloses a space right here, but then has kind of this open, non-enclosed space over here. That's why it is not a polygon. And of course, this oval is not formed by line segments. So let's look at a few more attributes and characteristics of polygons. Okay, here we have a table classifying polygons based on the number of sides that they have. So 3 sides is a triangle, 4 a quadrilateral, 5 a pentagon, 6 a hexagon, and you can see the list goes on. 7, 8, 9, 10, 11, and 12. Now beyond 12 sides, we just call our polygon an n-gon. All right, so based on the number of sides. So for example, if a polygon has 96 sides, we would call it a 96-gon. Okay, so 13 or above, you use the number -gon. All right, let's look at a little bit more on the next slide. Okay, polygons can be convex or concave. All right, so convex polygons. The definition of a convex polygon is any polygon whose non-consecutive sides can be connected by a diagonal, and that diagonal lies inside the polygon. So for example, I've got convex polygons here and here and here. Here's why they are convex, because I could pick any two vertices, and the diagonal connecting them or the segment connecting them lands either on the edge of the polygon or inside the polygon. So you can see all of those diagonals or segments in the case of a triangle land either inside or on the edge of the polygon. Whereas I've got concave polygons in each of the following, because I can, in some cases, connect two vertices, and the connection between those vertices falls outside the line, or outside the polygon, for example, that, or outside the polygon here. You can see the space, it lands outside of the polygon. So we've got concave, kind of caved in. You can see the space is caved in. And then we have convex. Okay, let's look at a few more attributes to polygon. Polygons can be equilateral. Equilateral meaning sides the same length. Or you could say that all sides are congruent. Or equiangular, angles, same measure. Okay, we can see in each of these, here I've got a rhombus, right? All sides are the same length. Here I've got a 1, 2, 3, 4, 5, 6. This is a hexagon, so quadrilateral. This is an equilateral, quadrilateral. This is an equilateral hexagon. Over here, I've got an equiangular quadrilateral, 90 in all four corners. And I've got an equiangular hexagon. What if a polygon is both equilateral and equiangular? If a quadrilateral, or any polygon for that matter, is equilateral and equiangular, it's called regular. So if you have equilateral and equiangular properties going on, you get a regular polygon. So a regular quadrilateral has a special name to it. Yeah, it's just a square. It's a square. Okay, we don't really have a special name for a regular pentagon, other than that it's just a regular pentagon. So all angles are the same, all sides are the same. We would call this a regular pentagon. Okay, and then a regular hexagon. Has equal angles, equal sides. We would just call that a regular hexagon. All right, let's continue. All right, let's talk about how we name polygons. When naming a polygon, list the vertices in consecutive order. So this pentagon that you see below here, we can name in a couple different ways. We could name it A, B, C, D, E. Or we could name the polygon any other consecutive order of these letters. So for example, I could start with D and call this the pentagon DE ABC, or any other where we follow that order. I would, of course, lead with the word pentagon, pentagon ABCDE, or pentagon DEABC. My spacing isn't great there, but typically you would, of course I ran out of space, you would write it in a way that would be pleasing to the eye, like the following. This would be preferable, so thank you very much. Okay, when we use it, name a triangle, of course we've got the symbol recognition available for us. We could go triangle STU, or triangle UTS, or triangle TSU, or any one of those right there. You can't screw up a triangle because, well, the order doesn't really matter there. Okay, let me go back up to the pentagon real quick. This would not be a way you'd want to name this pentagon. So please don't name it pentagon CDAEB, right? Because if I go from C to D to A to E to B, that's not in order, right? That's not in order of the letters, right? So make sure that you go in order. It doesn't matter where you start, as long as you go in order. All right, let's continue. Okay, let's talk about diagonals of a pentagon. Very important as we start to look at angle measures within a pentagon, as well as other properties. So a diagonal is a line segment that connects two non-consecutive vertices in a polygon. So name the diagonals of the following hexagon. Let's name them first by listing them. So how about M to T? We could call that MT, or we could call it TM. Hopefully you can see that yellow showing up. Okay, how about MH? Of course, we could do HM. I'm not going to continue in that pattern. MS. Okay, now I would switch to another vertex like A. Let's go from A to H, A to S, A to E. Okay, let's continue our list. Starting at T, let's go T to S, and T to E. I think those are all diagonals out of T. And then let's go to H and finish off with H to E. So if you look at this, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 diagonals. 9 diagonals. Each of those vertices should have 3 diagonals. coming from it. Let's name two sides now that are consecutive to MA. So here's side MA. Sides that are consecutive are those next to it. So I could look at the side next to it here, AT, and the side next to it, ME. So consecutive sides are sides next to some object, so AT and ME. Those are consecutive sides. Let's name two consecutive angles to angle S. So here's angle S. Two consecutive angles to angle S would be angle H and angle E. So angle H and angle E. Those are consecutive to angle S. All right, we got one more slide. Let's get to it. All right, kind of a hodgepodge of information today. We're going to talk specifically about triangles on this page. But let's look at what it means for two triangles to be congruent and what parts of those two triangles are congruent. So you can see labels here. I've got triangle ABC. And I'm being told that triangle ABC is congruent to this triangle over here. Now, what we want to do is we want to orient the correct angles to their appropriate corresponding angle in the other triangle. So it looks like angle A is congruent to angle X. Angle B is congruent to angle Y. And angle C is congruent to angle Z. Therefore, we could say that triangle ABC is congruent to triangle XYZ. Now the reason for the order of these letters is because angle A and angle X, those were congruent. Angle B and angle Y, those were congruent. And angle C and angle Z, those were congruent. So the order does matter. We would do not order them differently. That would not be true. ABC, triangle ABC is not congruent to triangle YZX. Okay, so as we look at side lengths, side length AB here would be congruent to side length XY. Now because A and X were congruent angles, we do need that order in that same direction, or that same order. It must be segment XY, not segment YX, right? Because angle A and angle Y were not congruent to each other. Angle A and angle X were. Therefore, segment AC would be congruent to segment X. Oops, let's go back. How about XZ? And segment BC would be congruent to segment YZ. All right, there's your lesson on introduction to polygons, some diagonals, and then some triangle congruence. We'll see you in the next video, guys.